All right, today we're going to talk about definite integrals and finding antiderivatives. So first of all, let's think about if we wanted to find a function with a derivative of 3x squared, what would it be? So it turns out that there is an infinite number of possibilities. For example, x cubed plus 1 is a possibility, x cubed minus 7 is a possibility, x cubed plus any old number could be a possibility, because if there's a constant and we take the derivative of that constant, it's just 0. So what we do in calculus is we use the letter c to represent any constant. So if you think of any number off the top of your head and add it or subtract it from x cubed. So let's say we made f of x equal x cubed minus 700. If we take the derivative of x cubed, we end up that f of x is 3x squared. And then no matter what this number is, what's the derivative going to be? 0. So again, in calculus, we use c to stand for constant, meaning when we work backwards, we don't know what that constant's going to be, so we use c as a placeholder. So this is general integral notation. Instead of writing what function has a derivative of f of x, we instead use this notation right here. And this asks the question, hey, what function has a derivative of this guy right here? So this reads as the integral, the integral of f of x with respect to x. And generally we say the integral of f of x with respect to x is equal to a larger function, an antiderivative, one level up, plus c. And again, c represents all the possible constants that we could tack on to the end of the original function. So something important, you must always write a plus c after your integral's answer to account for any constant in the original function. So in order to help you remember to do that, I've created a Padlet for you to put some funny memes to remind each other. So there's already a couple memes up there, but if you go to this website, you'll see some more memes to remind you when you integrate, always add a plus c on the back of your answer. So as we go through this, let's look at some rules. So the integral of 0 with respect to x, what does that mean? That means what kind of function has a derivative of 0. So we know that any constant has a derivative of 0. So 7 has a derivative of 0. 300 has a derivative of 0. Negative 1000 has a derivative of 0. So how do we write a catch-all for that? We use the letter c to say any constant has a derivative of 0. So we're working backwards. Given the derivative, what would the antiderivative or the integral be? All right, this next rule, if we want to find the antiderivative of k, where k is a constant, then it's going to be kx. And again, think about working backwards. If you have the function over here, f of x equals kx, what's the derivative of that? The derivative is k. So we're working in the opposite direction. Given k, we're going back to kx. And then again, you better tack on a plus c there. Next up, we've got k times a function. So here's the rule for that. Anytime you have a constant on the inside, you can take that constant and put it out in front and write it like this: k times the integral of f of x dx. And you've seen that rule before. We just want to revisit it. Same with these next two rules. We want to revisit them just to make sure you've got them in your back pocket and you're ready to go. When you see plus here, you can rewrite this as the integral of f of x dx plus the integral of g of x dx. Whoa, crazy line. And then here with a minus, you can write that as the integral of f of x dx minus the integral of g of x dx. And then this last one, how do we find the antiderivative? Well, let's ask ourselves a question. how can we work our way backwards if we know that the derivative is x squared? This is what I want you to keep in mind as we work toward an antiderivative. We know that the original function had to be something cubed, right? But remember, the power rule requires us to take that cube and bring it down into the front. So what we have to account for is the fact that we would need to put a 1/3 here. So when we take that 3 and bring it down, the 1/3 would cancel it out and we'd just be left with x squared. Let me show you another example of that. So another example would be if we had, I don't know, x to the 5th, and we wanted to find the antiderivative of that, meaning we wanted to go one level up. It would be x to the 6th power. But remember, again, when you use the power rule, you take that to take the derivative, you bring it down in front. So we would need a 1/6 here. So that way, when you take the derivative of 1/6 x to the 6th power, that 6 comes down, multiplies, and you'd be left with x to the 5th. So the general rule for that is this. The general rule is that the antiderivative is going to be to go one level up in your exponent, because when we derive, we go one level down, but then divide by that same exponent. There we go. Divide by that same exponent, and then don't forget your plus c. And that's the case when n is not equal to 1, because if n is equal to 1, that's just plain old x. So if that rule's feeling kind of shaky, it's okay, because we're going to look at some examples and start feeling really comfortable with this right away. Okay, so first of all, we've got a case of a constant right here with this 3. So we can take this 3, put it out in front. Let me zoom in a little bit. All right, so we can write this as 3 times the integral of x dx. So we want to integrate x, which means we're going to go a level up. What's one level up from x? X squared. But then we have to think backwards for a second. If we were going back, we'd take that 2 and bring it down. So we have to put a 1/2 right here. So that way, when we do take the derivative and we work backwards, we'd be good to go. And then that 3 out in front, I didn't leave enough room for it. So let me erase real quick. Keep that 3 out there, and then plus c. And we can rewrite this as 3/2 x squared plus c. So again, we're going backwards. Remember, when you take a derivative, like x cubed, you take that, you bring it back in front, and you get 3x squared. So when you integrate, you're going in the opposite direction. All right, let's try letter B. Again, we're going in the opposite direction. So first of all, let's ask ourselves if there is a way to rewrite this so that we can make it a little easier to work with. This is the same thing as the integral from or of x to the -3 power dx. So now let's think about working backwards to find the antiderivative. We know that it would have to be x to the -2 power because we're going up a level. So then what do we put in front to adjust? We need to put -1/2 out in front. To prove it, I'll show you. If we started with -1/2 and I ask you to differentiate this, you would take the 1/2 and you would bring it down here and you'd multiply those together. So -1/2 times -2 would give you just 1. So you'd be left with x, and then you'd go down a level, x to the -3, which is what we started with. So again, we are just working backwards. And then again, of course, we don't need to forget to put our plus c there. Did I do it on the other one? Yeah, okay, cool. So don't forget to put your plus c there. That's important. All right, on to the next one. Let's come up with a strategy here. Again, whenever you see a radical, I think it's always easier to write it as a rational exponent. So let's rewrite this as the integral of x to the 1/2 power dx. So now when you think about going up a level, if we add 1 to our exponent, that's going to be x to the 3/2. But then we need to adjust with a fraction and put that out in front. So what could we put in front of our x so that when we bring down the 3/2, we will multiply and get 1? Well, the answer is the reciprocal. If we multiply by 2/3, 2/3 times 3/2, they say goodbye to each other. And then again, don't forget to put your plus c out here. All right. Moving on to this next one. It's difficult to find the integral of things that are being multiplied. So what's always easiest in this case is to clean it up a little bit. Let's start by rewriting this as x to the 1/3 power times x minus 4. And that makes it easier to distribute that x to the 1/3 to each of these terms. So we're going to give it to this guy, give it to this guy. So we can rewrite this as the integral of x to the 4/3 minus 4x to the 1/3 dx. So now we can work backwards. So again, when we work backwards, instead of subtracting 1 from the power like we do with the power rule, we add 1 because we're undoing it. So if we add 1 to this first part, we are going to get x to the 7/3. Now remember, when you take the derivative, you bring the 7/3 down in front. So we're going to undo that with the 3/7. You're noticing that if you put the reciprocal there, it's always going to make that fraction out in front disappear. Now this one, a little bit different, but we got this. We want to have x to the 4/3 right here. But notice in our derivative, we don't want it to have a 1 out in front. We want it to have a 4 out in front. So what can we put in front of our function to make sure that we retain a 4 out in front? 4/3 times something gives us 4, and the answer to that is going to be 3. And then, of course, don't forget your plus c. I'm going to rewrite this again. 3/7 x to the 7/3 minus 3x to the 4/3 plus c. All right, for this next one, the plan is to use rational exponents again to make our lives easier. So we're going to start by rewriting this as the integral, and then root x, we can write that as x to the negative 1/2 power. The 1/2 makes it a root, and the negative puts it in the denominator. And then we're going to multiply that by the x plus 1 in the numerator, dx. And now we can do like we did in the previous problem and distribute this term to both of these guys. So we can rewrite this as the integral of x to the positive 1/2 power. Remember, you're adding an exponent of 1 there. So negative 1/2 and 1 make positive 1/2 plus x to the negative 1/2 power, and all of that with respect to x. So now let's go backwards again. For this first one, we want to go up 1 in our exponent, so 3/2. And then to get the constant of 1 out in front, or the coefficient rather, we want to multiply by 2/3. Plus, and then here again, we want to go up 1 in our power, so we're going to go to positive 1/2, and then we're going to put a 2 out in front. And then finally, don't forget your plus c to account for any constant that we antiderive. All right, let's try this next one. This next one, again, it's multiplication because this is really looking at t squared plus 1 times t squared plus 1 dt. And so it's harder to do multiplication. So what I would suggest is foiling this guy, multiply your binomials, and that way you can deal with just the sum of some terms. So we can write this as t squared plus 2, or sorry, t to the 4th, yikes, t to the 4th plus 2t squared plus 1, and then all of that dt. And now it's ready to work backwards. So we're going to have t to the 5th, and then a 1/5 out in front, plus t to the 3rd. Now keep in mind, your goal is to get a 2 out in front. So what can you multiply 3 by that will get you to 2? And the answer is 2/3. And then finally plus t. And don't forget your c at the end, that plus c. All right, let's look at example 2. We are given f double prime, we're given f prime, and we're given f, and our job is to find a general equation for f of x. So here we go. We are going to start with f double prime. So we know that the function f double prime equals 3. So how do we go up one level? How do we find what f prime is? Well, f prime is going to be 3x because it's one level up from this. Think if you found the derivative, if you went backwards, the derivative of 3x is 3. So we can't forget the fact, though, that there's some constant c here. Here's the crazy thing, though. We're given something we can plug in to f prime to help us figure out c. So if we know that f prime of 2 is equal to 3 times 2 plus c, and that equals 5, then we can work backwards to solve for our c value. So we know that 6 plus c equals 5, so c equals -1. So now we actually used our given point right here to solve for c. So we know that f prime, the function f prime, is actually 3x minus 1. So now we can do the same thing again. We can go up another level and we can just find regular f. So we're going to go up one level. We know we're going to have x squared now. So what needs to go out in front so that we can keep the 3 that we started with? 3/2 minus x plus c. Again, we can figure out what our c is because we know here that f of 2 equals 10. So if we plug in 2 for x, we should be able to get 10 out. So let's do it. If we know that f of 2 is the same thing as 3/2 times 2 squared minus x plus some value c, we know that has to equal 10, we can use our algebra skills to work backwards and find c. So here this is 3/2 times 2 squared, which is 3/2 times 4, and 3/2 of 4 is 6, minus 2 plus c equals 10. That's the same thing as 4 plus c equals 10, so we know that c is 6. So finally we can write our final equation, f of x, and I realize I've been neglecting the of x's here. It doesn't matter too much. But the final function f of x is 3/2 x squared minus x, and then over here we just solved for our constant c, which is 6. All right. So next we're going to use what we know about the derivatives of trig functions to find their antiderivatives. So again, remember, we're working backward. What function has a derivative of cosine of x? If you were given the derivative, how do you work backward to the original? Well, we know that sine of x has a derivative of cosine of x. But this time when we do antiderivative, we're not going to forget to put that plus c afterward because it could be sine of x plus 4. And when we take the derivative, that's still going to be cosine of x. So that c right here accounts for any possible constant we could have after our original function. All right, so what function has a derivative of sine? That function is negative cosine. Negative cosine has a derivative of sine. And again, plus c. So again, we're working backwards. What function has a derivative of cosecant squared? That's negative cotangent of x plus c. What function has a derivative of secant squared? That function is tangent of x plus c. What function has a derivative of cosecant cotangent? That would be negative cosecant x plus c. And then finally, what function has a derivative of secant tangent? And that is secant of x plus c. So keeping these rules in mind, we are going to find some antiderivatives. So we want to know what function has a derivative of this guy right here. We're going to work backwards. So the first thing I would suggest is noticing you have that constant of 2 that we can bring out in front. And so we can write this as 2 times the integral of sine of x dx. And now you can ask yourself, hey, what function has a derivative of sine? Well, I know that negative cosine has a derivative of sine. So you can bring that 2 along for the ride. And then negative cosine, I'm going to stick the negative here and put the cosine here of x. And then again, don't forget your plus c. So one more time for this guy. Now this one looks kind of crazy, but this is where your pre-calc training comes in. When you have sine of x over cosine squared of x, that should allow you to think, hey, there's a way for me to break this up into two different fractions. I can break this up into sine of x over cosine of x times 1 over cosine of x. Because remember, when you multiply, you go across the top and across the bottom. So that's the same thing as sine over cosine squared. And then all of this dx, of course, with respect to x. Sorry. There we go. Okay. So why was this helpful? Well, we know sine over cosine is tangent. And we know 1 over cosine is secant. So we can rewrite this guy as the integral of tangent x, secant x, dx. And that is a derivative we recognize. So how do we work backwards from that? The antiderivative, in other words, the function that has that as a derivative, is secant of x. And don't forget your plus c. All right, let's keep working backwards. What if you start with a derivative of an exponential function? Well, here's Old Faithful. We love this one. What function has a derivative of e to the x? You know it. It's e to the x. And then again, don't forget your plus c. This one's a little more complicated. What if your base is an e? What if you're finding the antiderivative of a to the x dx? The antiderivative is going to be 1 over the natural log of a times a to the x plus c. So let's use these rules to help us find the antiderivative of some of these integrals. So for this guy right here, first of all, hopefully you're getting in the habit of seeing that number and putting it in front of your integral. So that's 5 times the integral of e to the x dx. And now, what function has a derivative? So if that's the answer to what is the derivative, we know it. It's e to the x. So bring that 5 along for the ride. 5e to the x plus c. All right, so this next one, a little bit tougher, but nothing we can't handle. We are finding the integral of 6 to the x. So we use the rule. It's written right above. We're going to do 1 over the natural log of whatever your base is, in this case it's 6, times 6 to the x power. And again, don't forget your plus c. So that's just a matter of remembering those rules. All right, let's do anti-differentiation of 1 over x. So I want you to remember, hey, what function has this as a derivative? When we work backwards from 1 over x, what function do we land on? We land on the natural log function. Now, in the case of finding the antiderivative, we always just find the natural log of the positive values. So we do the natural log of the absolute value of x plus c. All right, let's do it. Example 6. So here we can rewrite this. This 5, again, can go out in front, and we can write this as 5 times the integral of 1 over x dx. And then we know that the antiderivative of 1 over x is the natural log of the absolute value. So we can write this as 5 times the natural log of the absolute value of x plus c. All right, so recall, we went over the fundamental theorem of calculus in a previous day. And so I want you to remember that when you see the integral from a to b of f of x dx, I don't know where that 2 came from right there. There shouldn't be a 2 right there. But anyway, the integral, trying to knock that out. Okay, the integral is going to be capital F of b minus capital F of a. And remember, that means that the derivative of capital F is lowercase f. So let's use that to get this done. So here we've got a definite integral, meaning we don't just have that integral symbol, we now have some numbers on the scene. So how do we deal with those? We get better at zooming. Okay, here we go. So first, find your antiderivative. What is the antiderivative of 10? The answer is 10x. Now, you might be tempted to put a c plus c here, and if you are, that's awesome. You should be in that habit. But when you're working with definite integrals, in other words, when you're working with numbers that you're plugging in, you don't have to worry about your plus c here. Instead, we're going to use the fundamental theorem of calculus, and we're going to do big F of 4 minus big F of little 2. And a lot of times you'll see that written as from -2 to +4. That means the same thing. So that means we're going to find 10x with a 4 plugged in, so that's going to be 40, minus 10x with a -2 plugged in, which is going to be a -20, and that leads us to 60. Let's try the next one. First, we're going to find the antiderivative, and then we're going to use the fundamental theorem of calculus to find the definite integral. So first, we're going to take the antiderivative of this. We're going to go up 1, and then remember we put that 1/3 out in front to adjust. Plus, and then we're going to think of this as x to the 1/2. So we're going to go up 1, x to the 3/2, and then we're going to put a 2/3 out in front to adjust. Again, if you're in the habit of putting plus c, I love you for that, but you don't have to here, because instead we're going to find big F of 1 minus big F of 0. So let's plug in 1 here. 1/3 times 1 cubed is... Here, I'll even write down what we're doing just so you can remember what this means. We're going to do big F of 1 minus big F of 0. So we plug in a 1. That's going to be 1/3 plus 2/3. And then we're going to minus, and we're going to plug in a 0, which ends up being 0 plus 0. So that's super cute. We like that. So 1/3 plus 2/3 is 3/3, which is 1. All right, next one. Again, we are going to find the antiderivative. So if you want to rewrite this with the 2 out in front, if that helps you out, go for it. I think it's a great idea. And then secant squared of theta d theta. And if that freaks you out, it's the same thing as an x dx. It's just a variable. So we want to ask ourselves, what function has a derivative of secant squared? And the answer to that is tangent. So keep that 2, and then tangent theta. And again, if you're putting plus c, I love you for that, but when you have to do definite integrals, we're just going to plug in pi over 4, we're going to plug in negative pi over 4, and then we're going to subtract what we get. So 2 times the tangent of pi over 4 is 2 times 1. Minus 2 times the tangent of negative pi over 4 is 2 times -1. So that ends up being 2 plus 2, which is 4. All right, let's keep going. This next one, looking kind of crazy, but let's rewrite this with rational exponents to make our life easier. So this is, or I just mean rational exponents, yes, but we can also split it up. Let's do it like this. We can rewrite this as 1 over root t minus root t over root t. So we're splitting it up because there's 2 pieces, we're splitting it. And now we can see that this is 1 over root t, and that's the same thing as t to the -1/2. And then here, root t over root t, that's just 1. So by splitting it up and rewriting it with an exponent instead of a radical, it's way easier to find the antiderivative. So remember, when we find the antiderivative, we go up 1 in our power. So this is +1/2. And then we think about what goes in front to adjust. We'll put a 2 here, minus t. And we're going to evaluate that from 9, or from 4 to 9. So we're going to find f of 9 minus f of 4. So if we find f of 9, we're going to plug in a 9 in these 2 t's. So we're going to get 2 times the square root of 9, which is 3, minus 9. And then that whole quantity minus 2 times the square root of 4, which is 4, minus t, which is also 4. So we're going to have 6 minus 9, which is -3, minus 0, which ends up still being -3. Oops, sorry. -3 minus 0 ends up being -3. There we go. All right, still some more practice ones. So this next one, not too bad. We love to see this as a derivative because we know the antiderivative, it's just e to the x. And we are going to plug in the natural log of 5, and we're going to plug in 0. So e to the natural log of 5 minus e to the 0 power. Remember, e and natural log are inverses, so that's going to be 5 minus, and anything to the 0 power is 1. So this gives us 4. All right, moving on to this next one. Don't let it freak you out that you see a 3 right here. Remember, it's a coefficient, so you can rewrite this integral as 3 times the integral of 1 to e squared over 1 over x dx. And now this should look more familiar, because what derivative, or what function has that derivative? The natural log function. Please remember to put the natural log function, or to put the x in absolute value brackets when you're finding the antiderivative. And then we're going from e squared to 1. So we're going to do 3 times the natural log of e squared minus 3 times the natural log of 1. All right. So the natural log of e squared is 2. Remember, natural log and e undo each other. So this is going to be 3 times 2. Minus, and the natural log of 1, you're asking yourself, e to some power gives you 1. That power is 0. So 3 times 2 is 6 minus 0, still 6. All right. So the fundamental theorem of calculus has an interesting byproduct that we're going to take a look at. And that's this. When we take the derivative of the integral, they undo each other. We've talked about this in class already, y'all, so don't panic when you see this. It just means that when you have a derivative and you have an integral, they undo each other. Here's the new take on this. What if you're finding the derivative from a to x? What do? For every x in the interval, you can take this x and plug it into that function, and you'll get f of x. Or if instead of an x, you have a function up top, like a function u, so let u be a function, when we take the derivative of the integral, you can plug u in there, but you've got to use the chain rule. That's going to be the function f of u times its derivative, u prime. So in other words, antiderivative and derivative are inverse operations. So the new part here is that you've not done this with a function here, either a function x or some function u. So this is the new thing we're going to do. And if writing this down kind of freaks you out, don't worry. When we look at an example, I think you're going to feel a lot better. So here's example 8. So here, for the first time, instead of seeing a number in your integral, you're seeing a function. That's what's new here. The good news is that when you have a derivative and an antiderivative, they say goodbye to each other. But what do we do with that function? We plug it in for t. So we can just write this as x squared plus 1, and we're done. So same thing here. We have, instead of just a number, we have a function. So what's going to happen? A derivative and an antiderivative undo each other. And then this function, x, just plugs in for t. So we're going to have 5x minus 3. All right, let's up the difficulty slightly. Here we have a derivative and an antiderivative. They're going to say goodbye to each other. And so we're going to take this function and substitute it in for t. Here's the thing. Earlier, you were working with just plain x. And what's the derivative of x? The derivative is just 1. So do we need to write that 1? No, multiplying by 1 doesn't change anything. But this is going to be a little bit different because this function has a more complicated derivative. So we're still going to write this function. We're going to replace t. So we're going to do 5x squared plus 1. But now we're going to multiply by the derivative of this function as well. So this is a chain rule situation. It's just appearing in a different way. So what's the derivative of this? It's 10x, and that's going to be your answer. You also have the option of distributing, so 50x cubed plus 10x is also sufficient. They're both the same thing. So remember, if you have just a plain x at the top of your integral, replace the t. And if you have more than just a plain x, don't forget the chain rule and multiply by its derivative. So same thing here. We have a more complicated function. So we're going to take the function, we're going to start by plugging it in for t, and then because it's more complicated, we're going to multiply by its derivative. So we're going to replace the t here. So 3 times 2x cubed squared plus 1. And then we're going to multiply by the derivative of that function. So that's going to be 6x squared. Sidebar, you might be wondering, what do I do with this 2 right here? And the answer is nothing. Don't worry about it. Just worry about the function at the top of the integral. So this answer, totally sufficient. But if you're like me and you want to simplify a little bit, you can clean up. First, we can take care of that exponent. So 3 times 4x to the 6th power plus 1. And all of that times 6x squared. And then you can clean up a little bit more, 12x to the 6th power plus 1. And again, all of that times 6x squared. And then finally, we'll have 72x to the 8th power plus 6x squared. Now again, in a short answer scenario, this totally fine. But remember, you're going to see multiple choice on your AP exam. So this is more likely what you're going to see. So I prefer that you get it down to this just so you're comfy knowing what to look for. But again, if this was an FRQ scenario, that answer would be totally fine. And you're done. Hooray!